Okay, so let's see another trick to further simplify the softmax derivatives, and it's a pretty common trick that we use. And again, this is a common trick that is commonly used in policy gradient algorithms, where instead of optimizing the probability for each action, or taking the derivative for each action with respect to taking the derivative of the probability for each action, we take the derivative with respect to the derivative of the log probability for each action with respect to each action. So how would that change? So this is the update, the action score update that we've seen so far, following the regular derivative, softmax derivative with this, of the probability for each action. And we replace, the trick is to replace the probability of a specific action, of each action AT, with the log probability of that action. And this might seem a bit weird, and you might say, I don't want to optimize the log probabilities, I want to optimize probabilities. And for now I would say, don't worry about that, it's kind of the same. I mean, we can optimize the log probabilities, and it usually converges or results in optimizing the probabilities, and it has a lot of advantages, as we'll see next. So let's see, how does the derivative of the log probability behaves compared to just the derivative of the probability. So let's say the derivative of the probability, just the probability is without changing it, without any function on top of it, can be considered as a straight line between 0 and 1, and you can see that the derivative is, well, constant between 0 and 1. It's only we only care about between 0 and 1 because it's probabilities, right? We can't go beyond that. And how does the log, the gradient, or the derivative of the log of the probability behaves? Well, it's very, very large, goes to infinity at 0, and converges or becomes less extreme as we approach the value of 1. So you can see that, first of all, the direction of this derivative is the same. That is, if you take a gradient ascent step on the probability or the log probability, the direction is the same. That is, it will, if you want to increase the score of your action, both of these will increase the score of that action, if you need to do so, right? If you need to change to the log probability, would result in the same update direction as a change to the probability itself. However, there are some differences. Specifically, if you're closer to a probability of 0, you can see that if the probability is close to 0, by the way, a softmax probability ensures that we never add 0, of course. The log probability is not defined for 0. It's fine. But if you are close to 0, and you can definitely get close to 0, well, the derivative of the log probability might be extreme. That's usually fine. It might be a problem, right? You might need to add some tricks there, or to add some epsilon. You might encounter that. I have a student that did, I can't remember on which project, but you might encounter some nuns there. But this can be easily overcome. And on the other hand, this might be very useful. So for instance, if you have an action with a probability of 0 or close to 0, a very low one, and you actually decide that you want to increase the probability of taking that action, well, now you have a much stronger indication or stronger step towards increasing the probability from 0 upwards towards something meaningful. Okay, so it can actually be pretty practical. But the main advantage of taking the log likelihood, of optimizing the log likelihood, is actually that it further simplifies the derivatives of the softmax function. So let's see how that actually occurs. So previously we saw how to compute the Jacobian, each entry in the Jacobian, for any ij action pairs, right? And we defined it as follows. If if you're taking the derivative of the same action, or of the probability for a specific action with respect to that same action, so I equals j, so this is this line, and if you're taking the derivative for a probability for some action I with respect to a different action j with the score with respect to the score of a different action j, so that's the bottom line here. Now, how will these change, these derivatives? How will they change if we, instead of taking the derivative with respect to the derivative of the probability, we will take the probability of the log probability. So I have the derivative of log here on the right, just the identity, the definition, just provided it. So the derivative of log of x is simply 1 over x. Now you might say, hey, listen, natural logarithm is not the same as any logarithm, but it's constant away, it's proportional to, you can still use logs, and then it might mean that you have to change your alpha. But in many cases, proportional to is just as good. So specifically, right, if you see our gradient descent step, you can see that the proportion can be mitigated with the alpha parameter. So proportional to is just as good as equal, in this case. And so, using that and using this identity and also using the not factor.
Chain rule.
The chain rule in derivatives, we see that the change to these derivatives is simply we take the same derivatives that we did previously, but now we multiply these by 1 over pi, which is helpful in further simplifying these derivatives, right? So now the derivative of log of pi with respect to h of j simply becomes either 1 minus pj for the case that I equals j, or minus pj for the case that I is not equal j. So even simpler once we actually try to take the gradient with respect to the log probability. And as we've seen previously, it won't change our direction of the derivatives, and it actually might be helpful if we're trying to escape the zero probability in many cases. So this is a pretty useful trick that we'll be using over and over again, where instead of taking the derivative with respect to the probability, we'll take it with respect to the log probability. Especially if we use a softmax function, right? So by the way, this is also common also in supervised learning, right? If you take log loss over multi-objective, multi-classification problems for supervised learning, this is also commonly done there. We update, or they usually in that discipline, they'll update the log probabilities, they'll optimize the log probabilities over a softmax activation function. If you're not familiar with that, don't worry too much about that, but I'm just saying this is a common trick throughout machine learning, and we'll see it later on. Okay, I will refer back to that later on. Okay, so now we take these new derivatives, the red one, right, the derivative with respect to the log probabilities, and we can update our update rule. So, right, previously we had these derivatives, and we said this is the update rule. So now, once we take these new derivatives, the derivatives with respect to the log probability, the derivative of the log probability, we can update our score update rules to be simplified, right? Here it's simply multiplied by y minus the probability of taking the action that we just took, and for any other actions it's simply multiplied by the probability of taking that any of the other actions. Okay, so going back to the question that Vabhav asked earlier, how do we set, or how should we set the baseline value? And the baseline value tells us if a specific outcome that we just saw, if it's a good outcome or a bad outcome, right? Would be above the baseline value or below the baseline value. Right, so this is what we said before. This is how we define a good outcome or a bad outcome. A good outcome that will increase the probability of taking that action. If it's a bad outcome, we'll reduce it. So it's pretty important question, how to set the baseline, right? So to answer this question, let's look at a specific example. So let's say we have 3 different arms to play. And the current score for each one of these arms, let's call them A, B, and C. Let's do A1, A2, and A3. So the current score for each one of them is given in the table here. So for instance, for A1, currently we have a score of 3. For A2, currently we have a score of 2, and so on. If you pass these scores into a softmax function, you'll get these probabilities. You're more than welcome to validate my values. By the way, sometimes I make mistakes, so you're more than welcome to validate. If you find a mistake, I'll give you a +1 to your final grade. And let's say that at the current time step, if we play action 1, we'll observe a reward of 2. If we play action 2, we'll observe a reward of 8. And if we play action 3, we'll observe a reward of 1. Okay, so how would the different baselines impact the updates that we're going to perform? Okay, so as before, and let's say we won't look at the second update rule. We won't, let's say that we're only considering the first update rule. That is, we're updating as if we would play the specific action. So for instance, what do I mean? If we are playing action number 1, then we'll observe a reward of 2, meaning that we'll update the score for A1 to be RT, or 2 minus the baseline value, multiplied by 1 minus the probability that of taking that action. Okay? We're going to update the value towards this gradient step. And let's assume that alpha is 1, so 1 minus this value. Okay, so how would this update look for different values? So if we'll set our baseline reward, the reward that we expect, to be 10, by the way, you can see that 10 is higher than any of the rewards that we might see. So this is a very optimistic value to set as a baseline. We'll see the following values post-update. Okay, so I'm just talking about the update direction, not the update value after. So if we play action 1 and see a reward of 2 and update towards this value here, we'll get 3 minus 2.68. Okay, again, feel free to take whilst I'm talking, take a pen and paper and just validate my values. +1 to your final score if you find a mistake. And you might find a mistake, right? Many times I do make mistakes. And then it will be 8 minus 1.51 if we would play action 2 and observe the reward of 8. And if we would play action 3 and see a reward of 1, we'll update the score here to be 1 minus 8.96, minus this value, right? If we would set, we can do the same computation and see what would happen if we'd set the baseline reward to be 3. And you can see that 3 is, well, something in the middle. If we'll have a baseline reward of 3, action 1 would seem bad, action 2, the action for action 3 would seem bad, but the outcome for action 2 would seem good. So that might be a good baseline reward to discriminate between the different actions. And if we set a very pessimistic baseline reward, then all of the actions scores will be updated upwards. So which baseline value would you say makes most sense?
I would say 3, because doesn't reduce the probability of the good action too much, and it's increased the probability of the action which is got a sorry, this has the highest score, but this has a good reward, it says, right? But here, yeah, this seems like the medium one, and the too negatively initialized one would maybe give positive values for all actions, making it unclear what's a good choice.
Okay, so what's your answer?
The 3.
3.
Yes.
Yeah, 3 seems like a good option because also it helps us discriminate between the different outcomes, right? So 3 seems to say, well, the good outcome is actually good. It's more than 0, right? R minus RT minus R minus the baseline is a positive value. But it tells you that the other 2 outcomes are actually bad. So it helps you discriminate between the best action and the not best actions, right? The other actions. So this seems like a good intuitive choice of a baseline reward. In general, a good choice here, a good practice would be to set the baseline reward as a moving average of all of the rewards that you observed so far. Okay, eventually it will converge on the optimal action reward if you choose that over time, if you gradually decrease exploration. And it's usually results in good performance. Without going too much into the math here, I'll just say that this is, as I said before, the baseline value is an important question, and later on we will revisit this question in later algorithms and rediscuss this issue of how do we set the baseline value, specifically in more general NDPs. Okay, let's see how setting the baseline impacts the learning. So this is the same problem as we've seen before, the same benchmark problem. These are the 10 bandits problem, right? We have 10 actions, we have one action that is better than the other, but all of them has some Gaussian for the normal distribution for the reward that we observe, right? With the sigma 1 and mu, different mu's. We would like to converge on the optimal action. As far as I remember, that was action number 3. And you can see what happens if we use policy-based, policy gradient approach that we just discussed with different baseline values. So if we set the baseline as indeed the average of all of the rewards that we've seen so far, we can see that this results in a better learning curve compared to no baseline, setting it to 0, or actually having no baseline, right? Removing it from the equation. And of course, your learning rate might impact the learning efficiency, okay? And this is usually a hyperparameter that needs to be tuned for different problems based on if you change the magnitude of the reward, the best alpha hyperparameter will also change, okay? So don't look at these results and say, well, yeah, a hyperparameter, a learning rate of 0.1 is always the best. No, that's highly sensitive and it's correct for this problem, but it changes for different problems. It will also change for this problem if I change the magnitude of the reward. Okay, so usually we just check different alpha values and report the best one. But the main takeaway here is that a good baseline, for instance a baseline that is the average rewards for all rewards seen so far, is better than having no baseline. And we'll see it also later with the more general NDPs.